Hey there, gang. In this video, I want to talk to you about transforming differential equations. So sometimes when you start with a differential equation, you have something that's quite complicated, and it may not be something that we have the skills to be able to handle. But with a little bit of mathematical trickery, we can transform it into something that we do know how to handle. Okay? And so let's go ahead and take a look at some examples of doing this. So one of the first things we're going to look at two types of differential equations. One's called a Bernoulli equation. The other one is called homogeneous equation. And the Bernoulli equation is named after Jacob Bernoulli. And here he is right here, this dapper fella. And he is from the 1600s, and he is most famous for his results in probability theory. But he also dabbled with differential equations, and you may hear the Bernoulli name mentioned a lot in mathematics and physics, and that is because the Bernoullis did a lot of work. There were a lot of them, and they were all doing a lot of work in mathematics and physics. So this is not the only Bernoulli, but this is one of many Bernoullis, and he is responsible for our Bernoulli equation. All right, so the Bernoulli equation looks like this. You'll note that, so P and F are functions of x, and you'll note that it almost looks like a linear equation. If this term weren't here, this is exactly the definition of a linear differential equation. But we've changed it a little bit. Now we have y to the power r multiplied by our function of x on the right-hand side, so it is no longer linear. Now it's only called a Bernoulli equation if that exponent r is not equal to 0 or 1. But if r is any other number, then it is called a Bernoulli equation. You'll note that if r is equal to 0, then this is linear. And if r equals 1, then then this is a like term with that, and you can collect that on the other side. And so it's a straightforward differential equation that we know how to handle already. All right. Now, and I also want to point out that r can be any real number. Okay. Don't think it's just integers. Okay. So how do we handle a Bernoulli equation? Well, I want to go through this by looking at a specific example. And I'm going to look at the Bernoulli equation y prime minus 2y equals xy cubed. Okay, so p of x is just negative 2, f of x is just x, r is equal to 3. So how do we solve this differential equation? Well, I'm going to take you through this, and I'm going to save some of the details for you, so you can pause the video and fill those details in. So be ready with a piece of scratch paper to do that. Okay, but let's get going. So the first thing that we're going to do is we're going to look at the homogeneous equation. So we're going to set all of this stuff equal to 0. Okay, that was a trick that we've looked at before, where we set f of x equal to 0. And when you do that, you get the homogeneous equation. I'm going to use y1 in place of y, because the solution to the homogeneous equation is not the same as the solution to the original equation, so let's not call it the same thing. So this is the homogeneous equation. Okay, and when you solve this differential equation, so I'd like you to go ahead and do that. Pause the video, solve this differential equation, and I'll count down from 3 and we'll reconvene. 3, 2, 1. Okay, you've solved it. Welcome back. And you've gotten the solution y1 equals e to the 2x. Probably with a constant in here, right? Multiplied by a constant. Turns out, though, as we discussed before when we deal with the homogeneous business and variation of parameters, you can set that constant equal to 1. So let's just set it equal to 1. Okay? So here is a homogeneous solution with the constant equal to 1. And so what we're going to do with this is we're going to use this to help find our solution. And if you remember what we were doing with variation of parameters, we were saying that we were guessing that the real solution to our original differential equation might be this multiplied by another function. So we're going to go ahead and do that. All right, so we're going to say y equals u times e to the 2x. And when you do that, you can compute y prime. y prime is equal to u prime e to the 2x plus 2 times u e to the 2x. That's just using the product rule. Okay. Now, I'd like you to substitute this and this into that differential equation, and just like in variation of parameters, some things will simplify and you will get to what we're going to write down next. So I'll let you do that on your scratch paper. So 3, 2, 1. Okay, welcome back. So let's compare what we got. When you plug this and this up there, right, what you're going to end up with is this. U prime, u to the minus 3 equals, let's see, I think you get a x e to the 4x. Okay. So what we've done is we've substituted in the u's in place of the y's now. So now we have a new differential equation in terms of u. And just to simplify matters, let's multiply both sides by -2. Okay. The reason I'm doing that is because it'll make it easier to anti-differentiate the left-hand side, which is what we're going to do next. The antiderivative of the left-hand side and the antiderivative of the right-hand side. So go ahead and do that. 3, 2, 1. Okay, welcome back. Let's see if we got the same thing. This, when we anti-differentiate, we just get u to the -2. And when you anti-differentiate this, you get the following. This constant we cannot just assume is any particular value. This one we're going to need. All right, so we've solved this. Well, we solved it for u to the -2, but we can solve this for u. So I'll just do a little bit of algebra here. U is equal to plus or minus the following. This is raised to the -1/2 power. Okay. And we're almost done. Remember what u was. Sounds like bad grammar. What u was. What u was is u was from up here, right? So if you want to get back to y, we just multiply each side by e to the -2x, right? So this is really, so what I'd like you to do now, I'll count down from 3 again. We're going to substitute this stuff back in and get the y's back, all right? And then you're going to solve this for y. So we're going to plug this stuff down here, write this in terms of y, solve for y. Okay, so 3, 2, 1. All right, let's check our work. When you do that, you get the following. And we've got the solutions, right? We have a one parameter family of solutions. So, and there's actually two, either when you take the plus or the minus. So depending on the initial condition, one of those will be the valid solution. All right, so if you look through what we did, it's really just the same as variation of parameters. It's really no different than that. Variation of parameters typically only works on a linear differential equation, but it turns out that this one is close enough to being linear that it still works. Okay, so this is one of the things that you get used to in differential equations. That's why we're learning all these methods. We're finding some that work, and in the real world, when you go find a more complicated differential equation, you'll know the type of things to try. So even though this wasn't linear, try it. If it works, great. Then you got your answer, right? One more thing I wanted to say here. Forgot what it was. Okay, so we'll move on. If it reoccurs to me, we will come back. Okay, so so there we go. That's the Bernoulli equation. The next equation I want to look up is called a homogeneous equation. Now this is very confusing. And it's not my fault. It's just the way, it's a very unfortunate circumstance that happened in the evolution of differential equations. I'm not talking about this. When I say homogeneous equation now, I'm referring to something different. And the fact that it has two different meanings is very confusing, but unfortunately, that's just the way it is. Okay? So, homogeneous differential equations so this is not the same as the homogeneous that we mentioned before, not that they're equal to 0. Another usage of the word homogeneous is that the differential equation can be written in terms of y over x. Okay? Okay, this is not the same as the type as homogeneous as it was used on the last page. All right, and I know that's confusing, but that's just the way it is. So let me show you a differential equation that can be expressed in terms of y over x. Okay, let's take a look at this one. Y prime equals this stuff. Now you might be saying, wait, what? Where's the y over x's in here? Well, it may not be immediately obvious, but we may have to use a little bit of algebra here. So let's go ahead and do that. Let's distribute this x squared through. And we see that we really do have y over x squared plus y over x plus 1. There are y over x's in here. And when you have y over x's like that, one natural thing to try is a substitution. So what we're going to do is we're going to substitute u equal, you guessed it, y over x. Because that will just make these into u's. Okay, but we've got to figure out what y prime becomes. Okay, so if you solve this for y, we can compute y prime. Maybe I'll go back up to the top here. Y prime is just u prime x plus u, just using the product rule. So plug this stuff in to this differential equation and write it in terms of u. Okay, so go ahead and do that, and I'll meet you back in 3 seconds. Well, my 3 seconds. You can take longer. Okay, so pause the video. 3, 2, 1. Okay, so we're back. So after you plug this stuff in, it becomes u prime x equals u squared plus 1. Okay, plug that stuff in, do a little bit of simplification, and that's what you get. And what kind of differential equation did we end up with? It's a separable differential equation. I can get all the u's on the left and all the x's on the right using a little bit of algebra, right? I can write this as u prime over u squared plus 1 equals 1 over x. So this is a type of differential equation that you know how to solve. So go ahead and solve it, and I'll meet you in a little bit. So pause the video. 3, 2, 1, and you should have gotten, when you solve this, u equals the tangent of the natural log of the absolute value of x plus c. Okay, you should recognize that when you antidifferentiate this, you get the arctangent, but then when you solve for u, you invert that and end up with tangent. Okay, so we have our solution. So it's in the homogeneous equation, it's written in terms of y over x, and the substitution is obvious. I mean, if I'm seeing a lot of those appearing, why not let u equal that thing, right? And you might see something similar to that come up. you know, if you had a differential equation of the form, you know, y prime equals e to the I don't know, 3x plus 4y. Well, you know, there's a lot of stuff up here. Why not just make the substitution? Oops, that's not how you substitution. Substitute. Oh man, I'm losing my my writing skills here. Substitute u equals. Guess what we're going to write here? Well, just all that junk. 3x plus 4y. And you can compute u prime, plug it in, and that might be a good way to approach this type of problem, right? It might make some simplifications. So that's something to try. I invite you to go through and finish that one. So it doesn't have to be just a y over x. That's the point, all right? If you see something in there that's complicated, try making a substitution. Maybe it'll simplify the differential equation and allow you to solve it, right? This is just like u substitution in calculus when we did integrals. All right, so these are just the things I wanted to talk about today. Transforming differential equations by making substitutions. So you can start out with something that's quite ugly and end up with something that's quite manageable. Okay, so I hope that was helpful for you. I will see you in the next video.